Welcome to Longevity by Design, a podcast designed to give individuals access to the leading scientific information in the field of longevity. The ability to add years to your life and life to your years needs no opinion. Join us as we ask science to take the wheel. In each episode, Dr. Gil Blander joins a co-host and an industry expert in the field of longevity, shining a light and getting the answers to the key question: how can we live a longer, healthier life?
Hello, I'm Ashley Reaver, and I'm joined by Dr. Gil Blander. Welcome to Longevity by Design, How to Live a Longer, Healthier Life. We're produced by Inside Tracker, your science-based guide to optimizing your body from the inside out. Our guests today are Dr. Alex Zhavoronkov and Dr. Deepankar Nayak. Dr. Zhavoronkov is the founder and CEO of In Silico Medicine, as well as the founder of Deep Longevity. At In Silico Medicine, their mission is to accelerate drug discovery and development by developing new AI technology. Inspired by the work done at In Silico Medicine, Dr. Zhavoronkov started a second company called Deep Longevity, which specifically focuses on biomarkers of aging. Deep Longevity has built a number of patented aging clocks that predict biological age in many different ways, including mind age, blood age, microbiome age, and epigenetic age. Dr. Zhavoronkov has a PhD in physics, with one of his main research interests being the racemization of amino acids and proteins in the course of aging. He is joined today by Dr. Deep Nayak, the CEO of Deep Longevity. Both In Silico Medicine and Deep Longevity are rooted in science and leverage biotechnology to grow the longevity industry. Thank you both for being with us today.
Thank you for having us. Truly amazing to be on Inside Tracker, because I follow the company and the science and the community for a long time. Admire Gil's work, and I think that what you're doing is great. Happy to be with you.
Thank you,
Pleased to be here.
Thank you, and likewise, we are really excited, and I was really excited to meet with you a couple of weeks ago in Europe, and talk with you, Deep, a few weeks ago as well. And this is a real pleasure, and we love people that are pioneers and pushing us to the edge. So great having you. And we always like to start with the beginning and basically know what made each of you to become a scientist, and why to be a scientist that's studying aging.
So sure, I'll go first, I guess. I was very interested in aging since the very early childhood, because the traditional paradigm where you grow, develop, reproduce, mature, take care of your young, and then decline and die did not really appeal to me, especially the declining part, right? Dying is fine. And I was born in Latvia, but during the time of the USSR, when it just collapsed, and I grew up when it collapsed. So there were not really many opportunities for me to go into biomedicine right away. So I decided to pursue a career in information technology, and immigrated to Canada, did my first 2 bachelor degrees there as well, computer science and information systems. And then worked for a number of years in the semiconductor industry in the same kind of area that is now powering the deep neural networks, artificial intelligence of today. And in early 2000s, I made enough money to be able to sustain myself for a while. I decided to pursue my lifelong dream, which was going after aging and into longevity. But instead of just becoming an investor or supporting this industry in some other way, I decided to go 9 yards. So did my graduate work at Hopkins, and then also did my graduate work at MSU, built the machine learning team that is focused on longevity, and decided to focus on drug discovery as kind of one of the most credible ways to get into longevity. But I think that longevity is perhaps the most important area to focus on in general for anybody, And I'm not only talking about personal longevity, I'm also talking about longevity biotechnology as a cause, because if you discover a drug that can extend healthy life for everybody on the planet just by 1 year, so quality adjusted life year, you generate 8 billion quality adjusted life years. So that is the most altruistic thing anybody can do. And of course, we want to live longer. So it's great to be at the forefront. And I'm very happy to share some ideas with you today. But that's how I entered the field.
What about you, Deep?
Yes. So first thing which I'd like to say is that I am an engineer and an MBA. So I'm not really a scientist, but I have been a student of science. I have sort of spent my career with life sciences companies, helping them build and adopt technology. And that's sort of what I bring to the table at Deep Longevity, where we have a lot of novel science that we are creating. And then the idea is now we actually execute on that, take it all on the cloud, and then help various industries benefit from these diagnostic measures that we have built. So that is my goal. The field of longevity is fascinating, not only because, like Alex said, we do not want to be declining, right? It is just not about living longer, but about living healthier. And we are finding out that as we do more research, like in any area, the application of the research is far and wide. And hopefully we are also going to contribute to that body of science via Deep Longevity.
Awesome. I hope this first question is a softball for both of you and a really easy one. How does AI or artificial intelligence help with predicting health and longevity?
So AI can help for longevity in many ways. Well, longevity biotechnology. First of all, AI and specifically deep learning is a very good technology for tracking minute changes during the person's lifespan, in time in general. So we do not take aging as something that happens quick, right? So diseases happen quickly and you can notice them, but aging transpires over long time frames and we get worse gradually, so we do not really notice that. AI can be trained to be with, while it's with you and collecting the data at every point in time, training to predict your age using many different data types, right? So there are many data types that are changing in time. So for example, the picture of your face changes in time. AI can predict the age of your face better than humans do, right? Because you can train AI on millions of pictures annotated with age, it will recognize human age from pictures better than humans do. But there are many data types that are not comprehensible to human intelligence, like, for example, gene expression or protein expression or MRI images or CT images or pathology images or different molecular metabolic data. So you can train machines to predict age from the data that we cannot comprehend and then derive valuable biological insights from the AI that is trained on this data. So you can basically see what makes you younger or older compared to your chronological age and derive those most important features from AI. You can actually ask AI to help interpret why it thinks that you are older or younger. And then you can take those biological features that you derive from AI, you can put it into biological context, into groups of genes, for example, try to connect those many data types. So for example, pictures of the face and expression of the genes over time, and try to create those intimate links that will help you establish the cause and effect between the changes in different data types. For example, you may be able to identify the role of a specific gene that is being expressed at any point of time, and link it to a specific phenotype, to the representation of your body at any given point in time, and see if that gene contributes to you looking older or younger. And then we can try and manipulate this gene using small molecules or biologics or some other technique, so using a therapeutic. And actually, that's where AI can help a lot as well, because now we can substantially decrease the time it takes to develop drugs, to discover and develop drugs, both from the hypothesis generation, but also through the prism of small molecule generation. So you can also generate small molecules, drugs that have specific desired properties, and then you synthesize, test them, and put them into human clinical trials. That process can be substantially accelerated using AI. So AI can help you predict your age, also diagnose a specific condition, derive valuable biological insights, identify the mechanisms of disease, and possibly narrow it down to specific protein targets, and then help you prosecute those targets. So AI can help you all the way. Then it can also help you monitor the changes in those features that you've identified as being important when you're doing clinical trials on a therapeutic that you designed using AI. So there are many, many areas where AI can benefit. What Deep Longevity is doing, Deep Longevity is tracking aging in time using many data types, using blood tests, using voice, using even psychological data. So we can even use surveys, massive numbers of surveys, to train deep neural networks to predict human age in the absence of disease. We can call it psychological age, or predict another feature that actually animals do not have, which is how old do you feel? So it's actually subjective age. And then you can derive valuable insights, even psychological aging insights, to understand what makes you act younger or older, and what makes you feel younger or older. So we can also come up with specific recommendations on how to modify your environment, your mindset, to be younger and at the same time happier. Because actually, evolution makes you happier as you age. So it wants you to, those are some of the insights that we derived from our recent research in psychology. I can talk about that a lot later on. I'll actually, I'm not going to go into that right now. Maybe we can touch on that later, but AI can help you track aging at many, many different levels, and that's what Deep Longevity is doing. And AI, as I've mentioned, can prosecute some of those findings therapeutically, turn those valuable insights into therapeutic interventions, and that's what InSilico is doing. So our job at InSilico is to identify protein targets, generate small molecules, put them into clinical trials, and then sell them to the pharmaceutical industry. And of course, since I'm pretty much religiously dedicated to longevity research, we're trying to prioritize projects that relate to aging. So we're looking for dual purpose targets, proteins that are implicated in aging and disease at the same time. Again, AI can help you do that. So you can train on age and then retrain deep neural networks on disease status, and then look at common protein targets, common patterns that you can possibly intervene in and treat a disease, but at the same time benefit the patient from the perspective of extending healthy, productive longevity.
So that was very interesting, Alex. We are more trying to look at it from the angle of end user or end consumer. So the question that maybe I want to ask next is, why do you really need clocks for end consumer, and what is the value of the clock for the end consumer?
So sure. So our early research, when we started building age predictors using deep learning, and using massive data sets, we figured out that some people who look older than their chronological age, so much older than in their passport, usually they have some kind of problem. So either they're sick, or they are more frail, or they are pursuing a specific lifestyle or a habit that is likely to be detrimental to their health, and vice versa. So people who were predicted to be younger, they also looked healthier. Then we also used some of those clocks to see if people who are predicted to be younger, if they live longer. And it turns out that they live longer, and the probability of dying of any cause goes down pretty dramatically in every population we tested those clocks in. And also, if you are predicted to be significantly older than your chronological age, also the probability of dying of any cause goes up. So why those clocks are important and interesting to the end user, to the consumer, is because, well, first of all, it gives you kind of an umbrella view of your health, right? So you are your age. And on every data type, on every different data type, you are your age. So for example, if you just you look significantly older on pictures, it does not necessarily mean that you will have some biological problem, but maybe you are going to be less attractive. You will actually look older to yourself in the mirror. That will lead you to behave older and acquire new habits that will make you older in general, and also lead to early demise. But that's, I'm talking about pictures, on blood tests, on tissue-specific biopsies, on psychological survey data. We see similar results, right? We see that if you are predicted to be older than your chronological age, usually there is some kind of problem. And we want to fix this problem. And we also want you to ideally correct your behavior or look for an intervention that would make you maximally younger. So as young as possible without substantial side effects. Of course, on pretty much most data types, you would not be able to reverse aging by, let's say, 20, 30 years, right? It's very difficult. But AI can also show you to which extent you can possibly reverse either closer to your chronological age and your current health state, or even become substantially younger without damaging yourself substantially. So that's where I can help. And that's what I, as the end user, would really like to know. I personally do not use biological aging clocks as often as I should. I must say that I also, of course, monitor my biomarkers, but I should be testing biology more often. What I started doing much more often now is I started relying a lot on psychological aging clocks, because it's actually fun. And I didn't know anything about psychology just, 3-4 years ago. Only when we started building those aging clocks, I started learning about the modern theories in psychology, in behavioral psychology, and lifespan psychology, learned about social emotional selectivity theory, actually fun theory if you like to talk about it. It's a theory which kind of postulates that the shorter you expect to live, the older you are going to behave. And also that your psychological age is plastic, so you can actually manipulate it. It was developed by Laura Carstensen at Stanford, very famous scientist in psychology, and also reinforced by Helen Fang out of the China University of Hong Kong. So together they kind of took this theory to the level where it became very acceptable. And what we are looking at is changing the theory the other way. So the longer you expect to live, the younger you are going to behave. So I'm trying to test this theory on myself right now. So I am turning 44, trying to feel 29. And when you go deep into AI and start deciphering those aging clocks and looking at ways to get psychologically younger, you learn new tricks to kind of convince yourself and strategically deceive yourself to achieve that goal and also feel happier. So I like to be happy. So I'm not exactly optimizing now my biology, but psychology is also up for grabs. And it's also, it's slightly easier. And I think that there is a positive feedback loop. So you also feel a little bit younger. But I think that the insights that we're going to derive from psychological aging clocks are also propagating into biology, because the methodology, the AI methods that we're developing are very similar. So you train this aging clock, try to understand the key features that affect a certain outcome, and then you try to intervene. And then you also try to see how far you can intervene without breaking. And also try to find the optimal path for the intervention. So we try to do that to pretty much every data type, but psychology turned out to be the most plastic, and also, I hope, without any side effects, right? Because we will see. So if I develop schizophrenia or some other disorder, please let me know. But yeah, those clocks are very useful in consumer hands. At least they're useful to me.
Maybe Alex, I thought I can give an example in terms of how concrete use case of how it can actually, and we are helping consumers and having those discussions with the industry, right? So, and to your first question as well, one place where AI definitely makes a big difference is when you have multitude of data. You have a number of data points that you need to be reconciled, and it's just too much information for the human mind to process. So we have blood age at deep longevity, and blood age we use to predict the biological age using a clinical blood report. Now we need the blood report to have about 45 biomarkers, which gives the complete blood profile. Now the discussion that we are having here, for example, with the insurance industry is, we think they are ripe for transformation, and we are telling them that they should actually stop considering chronological age as a measure when they are doing their underwriting, when they are doing their pricing, and actually look at biological age, which is a far more accurate measure of a person's health. A 45-year-old who is taking care of his or her health and is eating well, sleeping well, doing exercise might belong to a cohort of 40-year-old. And vice versa. And one who is not might actually, the blood work would, and that's what our algorithms show, would resemble a cohort of 50-year-old, and they should be treated as such, because if they are not healthy, then they are at risk. And that is something which is going to and should be affecting their insurance premiums. And then as a consumer, if I'm one person who's actually taking care of my health, I would like to have that conversation with my insurance provider that I would like to be treated better, and I'd like to be given a favorable deal because I can show you through my blood work that I am healthier. So I thought I'd share that example.
And deep longevity has a lot of these different clocks. So photo age, mind age, blood age, microbiome age, epigenetic age. What exactly kind of are you testing in order to develop these clocks? And I think importantly, do they speak to each other? So can you get a larger picture by incorporating inputs from all of these different clocks that you've developed?
So great question. And that's what we're trying to answer. Many of those clocks are, of course, talking to each other because they are very related data types, right? So for example, if you look at several different methodologies for measuring methylation data, you'll see significant correlation between those clocks, right? Because one data type, just different ways to measure. Many different blood-based aging clocks also move in the same direction because they have similar features or features that are deeply correlated. But things like, looking younger, for example, so pictures and epigenetics do not necessarily move in the same direction. So people may look older, but at the same time on different levels, be younger biologically than their chronological age. Usually on a macro level, so being younger or older, many of those clocks move in a different direction. Sorry, in the same direction. But what you're really interested in is how do those clocks respond to different interventions. So, for example, if you change the diet, are you going to see a reduction in epigenetic clock, transcriptomic clock, blood-based clock, imaging clock, psychological clock? And the answer is no. They are very, so there the response is very, very different. So some of those interventions, they have to be clock specific. And for example, if you want to look younger to the camera, all you need to do is to put some makeup on. Is it going to make your epigenetic profile younger? Well, most likely not, right? As a matter of fact, over long term, it might, because again, to yourself, you will feel younger and you might, to some extent, have a positive feedback loop where you will also biologically become a little bit younger, but the effect should not be substantial. But yeah, many of those clocks, they just do not correlate with each other, and you need to design them and develop them so they are built for a specific application. So now we understand that if you want to develop a clock for a specific intervention, it is better to even derive that intervention from a clock. So one huge experiment that I'm doing at Insilico, we have one therapeutic program where we derived the target of the therapeutic program, the protein target, from the aging clock. So we took one of the most important features from a transcriptomic aging clock. Look at how this gene at that time, so feature gene, how this gene is also implicated in different diseases, looked at how it's implicated in fibrosis, and started the discovery program. So now it is in phase 1 human clinical trial. And, my, of course, greatest wish is to test it in phase 2 with the same aging clock that it has been derived from, to see if it reverses the aging clock that is a transcriptomic aging clock. Some of those questions require decades to answer. So even though you are using AI and you have vast amount of longitudinal data available, so lots of time series data to perform those experiments, very often to perform a very clean experiment, you need to do a prospective study. Prospective study is when you predict, wait, and then see what happened. And some of those studies will require years or even decades. So it's very difficult to answer this question right now, how those clocks are correlated with each other, and especially how do they respond to different interventions. But that's why we have deep longevity, and we do a lot of those experiments. That's why I think that partnering with companies that are in this field for the very long term and that are working with massive numbers of people and the data and are also looking at science-based interventions, companies like Insight Tracker, for example, is extremely valuable for just advancing this field forward in general, because again, answering those questions retrospectively is very often impossible. You need to do prospective studies.
So Alex, as you know, there is a lot of hype about the epigenetic clocks. and a lot of companies taking it to the market. And there is a lot of, I want to tell you that I'm a bit confused about what epigenetic clock really measure. And when we met in Copenhagen a few weeks ago, we also discussed it. And one part that made me very confused is a comment of Steve Horvath about the implication of methylation in a specific loci of the genome, that actually, as of a few weeks ago, there is not a strong correlation between the epi or hypomethylation of a specific loci and the transcription of the genes that is close to that. So can you maybe, as an expert in the field of the clocks, give us your insight? What are the epigenetic ages really saying, and what is it really measuring? Is it really aging or maybe something else?
Gil, you caught me right here, right? So I need to be very careful with how I answer, because many of the people who are working in the field of epigenetic aging clocks and the applications of those clocks, of course, the founder of the epigenetic aging clocks, Stephen Horvath, I have huge respect for him, and I hope and pray that he is going to get a Nobel Prize one day for epigenetic aging clocks, but also for many other things. So I need to be careful with this kind of prelude. I must say that currently we don't know what they really measure. So it looks like there are several components to those clocks. So from one perspective, there is some trace of evidence that it measures something in aging, right? So because, for example, many cells become more mature during aging, and we get less and less cells that are less mature. So in my opinion, what epigenetic aging clocks measure the most is the level of maturity of the cells. So how far are they from the embryonic stem cell state? So at the embryonic stem cell state, you've got a lot of methylation there, right? So the genome is very methylated. And many of those methylation patterns are being lost as the cell becomes more differentiated and more mature. So during senescence and also during differentiation, you see substantial changes in methylation patterns and mostly loss of methylation. So most likely, intuitively, I would say that methylation aging clocks measure differentiation and maturity, cell maturity, more than the general state of aging, or what we call biological age of the organism. So at this point in time, even though many companies are commercializing those clocks, the number that you are getting back is not exactly super valuable. So it is actually quite correlated with when you're going to die. So it is predictive of mortality. And there are many, many studies showing that. And it does look like it's more predictive of mortality than your chronological age. Is it because of aging or because we're measuring maturity of the cells? Hard to say. And should we use those clocks as a unit of measure of some intervention, of effect of some intervention? I don't think we can do that yet. So it's a little bit too early, even though those clocks have been on the market for a while. So I guess some people decided to forego the basic science, right, and answering many of the questions that remain unanswered, and start commercializing those epigenetic aging clocks a little bit too soon. Another problem with those clocks is that they're not exactly interpretable. So most of those methylation sites, and in the original aging clock that Stephen Horvath published, it's 353 methylation sites, and also in many other clocks, even the clocks that we've developed using deep learning that use the entire methylome, it looks like those methylation sites that are more predictive of the chronological age, they are not exactly located in the promoter regions of any of the important genes implicated in aging and longevity. So you cannot really directly ping them to a specific biological process or expression of a specific gene or a specific target. So it's very hard to interpret those clocks. We know that those very important sites are there. We know that they are very predictive of chronological age, but are they useful? It's very hard to say. So what we really need to be able to answer this question are paired matches of methylation patterns and gene expression patterns. And well, not only paired, you need to have multiple different data types collected at the same time from different tissues, from different people over time. The golden data set, in my opinion, would consist of epigenetic data, gene expression data, proteomics data, high resolution imaging data of those cells that we're looking at or tissues, and preferably a lot of data about the patients, where this data got derived from. And that would be able to answer those questions. Are specific methylation sites related to expression of individual genes? Are they related to specific phenotypes? Currently, we don't know. And I think it's a little too early to proceed with methylation clocks as the main data type for making those decisions. I think what you guys are doing at Insight Tracker, you're using blood tests, right? They are much more interpretable. They are much more interpretable by a physician because physicians know, and dietitians, they know that, if your level of glucose is high or higher, and also your level of albumin or a specific type of albumin is lower, it can be linked to a specific behavior, to a specific condition, and to a specific treatment. With methylation clocks, you cannot do that.
Yeah, no, I'm absolutely with you. And I like also what you discussed before about the transcriptomic clock and the proteomic clock, because then you are much closer to the end product. Epigenetic, it's very exciting, but it's a new, and I'm not sure that, as you said, I'm not sure that we really know what does it mean. And we need to be, as a scientist, we need to be very careful not to confuse the users, because I'm confused and I'm a scientist. But Alex, I wanted to ask you a follow-up question about, maybe it will make us even more confused, but about organ clock or organismal organ age. Because the question is, if you do clocks or measure aging clock for specific organs, are they age the same pace? And if not, which one is aging faster and which one is aging slower?
So for sure, there are multiple studies right now that are already published, and some will be published in the near future. I reviewed a bunch of papers recently, and also there are papers on archive. So people are started looking at organ-specific aging, both on methylation level and other levels, also proteomics. And it does seem like many of those organs age at different rates. Different clocks show completely different stories and different rates. There are some clocks that can be deconvoluted into organ-specific aging clocks, right? So actually, even like regular blood tests could be quite useful for measuring organ-specific aging, because some of those features in the blood tests, they can be directly linked to the function of a specific organ. Again, different studies tell you different stories. My personal opinion is that the tissues that get recycled and get regenerated the most, where you've got a lot of cell death and cell renewal, like liver, like lung, like kidney, I think they age faster. And that's what many different aging clocks show, predominantly epigenetic aging clocks. And that's something that is also very intuitive, right? Because that's where you've got a lot of change in in different cells, right? So they just die quickly and they regenerate. And as more and more cells die and regenerate, you've got all kinds of extracellular damage, right? But also the cells are more mature over time, right? So you get more damage accumulation in those cells. And also those same organs, they drive and contribute to the aging processes in other organs and systems, right? Because the faster your lung ages and the older your lung is, the lower is your lung capacity. And you don't get the same level of oxygen in other tissues. Same is true for liver, so it cannot process all the nutrients and toxins properly. Same for kidney. And you've got many processes that are triggered by those organs in other organs and systems. So organ-specific aging clocks are extremely important. We need to have more of them. I think that the simplest clocks are the imaging clocks coming from MRI, for example, and other tools that can non-invasively look at the organ. Even if we look at calcification, extracellular matrix changes, those data types provide you with very valuable insights into individual organ aging. And I again think that you need to combine multiple data types for each individual organ and look at how the data types are correlated in different clocks, even on kind of on the macro level. That will give us more insights. And also from person to person, the organ-specific aging rate, I think, varies quite a bit. So some people are just more resilient on specific levels. We see it in skin, we see it in hair, we see it in our eyes, right? It probably is true for many other internal organs, but currently there are no great studies to be able to reference that look at organ-specific aging in depth. We need to have more of those, even in mice.
And if we hone in on one of those, in particular, mind aging is something that there's a clock for. How can we optimize mind age? What are some of the things that you've learned or insights that you've gained that can really have an impact there?
Great question. So what we did for psychological aging clocks, we built them using different populational survey databases. So our first one was developed using a database called MIDAS, Midlife Study in the US. So it's massive populational survey databases that again deep bow to the US government for making all the publicly funded research available for everybody to use. So you can take an open database with anonymized data, train a deep neural network and answer your questions. So one of those databases is MIDAS. So by the way, for all the scientists who are watching, that's a good database. Took us a while to narrow down the databases to that one. And in that database, millions of Americans are being asked different questions over time, over many, many, many years. So there are over 1,000 questions there. Of course, not everybody gets the same questionnaire, but there are many, many different questionnaires, millions of Americans over time, very diverse population groups. And what we did, we looked at the questions, the survey questions that are directly related to your aging, but do not directly relate to chronological age. So, for example, questions like how old is your spouse, right? Usually, well, if you already have a spouse and or if you still have a spouse, just having a spouse of a specific age, usually it kind of gives out your age a little bit, right? Or how many years you are out of the labor force or in the labor force, or how many years passed since you finished high school. So those kind of questions we remove. We also remove questions that are non-modifiable. So for example, age of death of parents. How old were they? You cannot change that, right? we only look at features that are within your control. So like, for example, educational level, levels of optimism, how do you perceive the environment, how many social connections you have. So we constructed a data set of questions that are modifiable and are not directly related to your chronological age. And then we constructed an age predictor, so a deep neural net that has one neuron on the output, which is age, and many, many neurons on the input related to every one of those questions, right? And then train this deep neural net on massive number of those answers. So, and built the predictor for psychological age, so that's chronological age in a healthy state, and subjective age, predictor of how old do you feel. The accuracy of both predictors was approximately 6 years, 6 something, and pretty consistent, robust predictors. And then we looked at which features contribute the most to the accuracy and which features can be perturbed to make you younger or older. And those features predominantly are related to your optimism. So how optimistic you are about the future. So it's optimism, it's education, it is, well, actually your overall well-being as well. But optimism is number one. And when we did the first study, we only used about 50 questions. Then we went and did many, many other studies and also started looking at what features are also correlated with the state of well-being. So what also makes you happy, right? Well, which features make you happy? And can we construct those predictor of psychological and subjective age of the features that are also related to your state of well-being? And we realized that we can. So we did this whole exercise again with a slightly different questionnaire, and showed that, again, optimism is the number one feature that you have to change. So now you can change this feature very easily by, well, strategic self-deception. So if you believe that you are going to live longer than you currently believe, so you stretch your longevity horizon, it really affects your psychological age. So that's one single individual feature that changes your psychological age a lot. Also makes you happier, right? Because if you think that you're going to live for a very long time, there is a lot of life remaining, you feel more comfortable. And at the same time, you behave slightly younger because you can take more risks. You can take longer shot bets, right? So you make different life decisions. You purchase differently. You invest differently. Another, of course, there are different types of optimism, right? So one is that there is going to be technological advances coming up, right? The world is going to get better, but also the state of your health. So one of the questions that is very important is how well do you think you are going to feel in the next 10 years, right? Like rank it 1 to 10. Are you going to feel worse or better, or is going to be unchanged? That is a very, very important feature. Then some features are dealing with life satisfaction. So how satisfied are you with your life? How sense of accomplishment, how much you have accomplished, how much do you think you have contributed to the society, social connections, so how many friends do you have, how close you are with them, can you share a secret with somebody, et cetera, et cetera. So many of those features that they are pretty plastic. So for example, if you see that you are older because you don't have enough friends, well, you have to get out a little more, right? If you don't believe that the world is going to get better than today, if you think that those billions of dollars are being spent in biomedical sciences, and those thousands of people, or even now hundreds of thousands of people who are entering the field of aging and longevity, as researchers, as scientists, and what Gil witnessed at in Copenhagen at the ARDD conference, it's the 9th annual. We saw high school students present their research, right, at professor level. So if I were to see their talk just 10 years ago, I would feel ashamed because they performed the research that back then was probably unachievable even for me without the use of AI. So that gives you a lot of optimism in the future, a lot of bright thoughts, and it gives you hope. So I think that, and not that I think that, I mean, we see it through the data, becoming more optimistic about your life, about health, about the world in general, is the best way to reverse psychological aging. And the future is much better than you think. Currently, the media is trying to make you believe that it's the opposite because we react much stronger to the negative compared to the positive. That's why it's constantly negative news. So CNN trying to keep you on your toes, right, and react negatively. So sensation after sensation after sensation. Oh, it's not bloody enough. Okay, let's show them something else, right? Oh, it's not sensational enough. Let's show them something else. But the world is getting better, primarily because of the technology, right?
Yeah, and Alex, I think that the point that you said about the news is a very good point, and we see it at our recommendation engine. So one of the most powerful intervention is think positive, don't watch the news, watch a comedy. Then you become a positive person. And by the way, I want to say that as much as I know you are a very positive person, I assume that we can predict that you will live very long. So
Oh, I'm
I hope
very.
that we are right.
It's just it's a surface, right? It's and also I just started using this tool that we've developed, so I became more positive. But I must say that once you understand what is happening in the media, once you start changing that media flow and adjusting your own content for yourself, becoming more disciplined about where you get the news and what you watch, you become happier and more positive.
Yeah.
So kudos to you guys for making this podcast, for example, right? It's much better to have this kind of podcast than, oh, you're going to have a disease, let us prevent it, right? Or let us cure it. And showing some weird images of, unhealthy elderly. A lot of people do that, right? So it's easy to grab attention, but it's not healthy for people to do that.
And I want to be respectful of your time because I know you've got places to go, but ending that top longevity tip of being optimistic, I think is a really great one. So thank you so much
subscribe
for
to
your
your
time
podcast.
today.
Read, everybody who is watching, read David Sinclair's Lifespan. I mean, he kind of ignored a lot of our work, actually completely ignored our work in that book. But I must say that's the best masterpiece that anyone can start with. And also Peter Diamandis, The Future is Faster Than You Think. That's a great book. And in general, get out more. I'm in Riyadh in Saudi Arabia. A lot of people have stereotypes about the region, but hey, they opened up, so it's not what you think. And they started with initiatives like Evolution. So they plan to invest $1 billion annually in aging and longevity, predominantly by giving it as grants to the US academics. So kudos to Kingdom of Saudi Arabia and for accelerating this wonderful field. And I must say that, again, the future is much better than you think. So do Insight Tracker and follow research. Yeah, come to the ARDD conference next year. It's going to be the 10th annual. Bring your high school students to see how the other high school students present. And, our field is the most exciting field living through its most exciting time.
Yeah, I couldn't agree more, Alex. It was a pleasure hosting you, and Thank you for coming.
And we look forward to exploring the research in the field of longevity each month with you and the leading scientists. For more info, please go to www.insighttracker.com/podcast.
Thanks for listening to Longevity by Design. Please subscribe to this podcast on Apple, Spotify, or YouTube. Longevity by Design is powered by Inside Tracker, a personalized health optimization platform that helps people improve their lives by improving their bodies from the inside out using personalized, science-backed recommendations for nutrition, supplements, and lifestyle changes. To learn more, visit insidetracker.com/podcast.